Inside the clean rooms of Taiwan and South Korea, a silent crisis has quietly halted the progress of artificial intelligence. We are told that AI chips are getting smarter because their brain-like transistors are shrinking. But that is a lie. The real bottleneck holding back the next generation of supercomputing is not the brain itself, but the microscopic copper straw we use to feed it. For decades, computing has relied on a simple division of labor. The processor does the math, and the memory chip stores the data. But as artificial intelligence models grew exponentially, they ran headfirst into what engineers call the memory wall. While processor speeds increased by thousands of %, the speed at which we can pull data from memory only improved by a fraction. To bridge this gap, engineers created high-bandwidth memory, or HBM. Instead of placing memory chips far away on the motherboard, they stacked them vertically and placed them right next to the processor on a thin slice of silicon called an interposer. But even this design has reached its absolute physical limit. The current state-of-the-art memory, HBM3E, operates on a 1024-bit wide interface. To push enough data through this interface to train modern models, we have to run the signals at blistering speeds. This creates a massive power penalty. Driving high-frequency electrical signals across these microscopic paths generates immense heat and consumes a massive chunk of the accelerator's total power budget. We are running out of physical space to add more wires, and we cannot turn up the speed without melting the silicon. To break through this barrier, the semiconductor industry is executing one of the most radical architectural pivots in its history, HBM4. The core breakthrough of HBM4 is a doubling of the interface width to 2048 bits. Instead of pushing data faster through the same narrow pipes, engineers are doubling the number of physical pipes. But doing this requires a fundamental restructuring of how chips are built. In every previous generation of high-bandwidth memory, the entire stack was made by memory manufacturers using specialized memory-making equipment. But memory-making factories are not designed to build high-performance logic. To handle a 2048-bit wide interface, the bottom layer of the memory stack, the base die, must be packed with complex routing transistors. This requirement has shattered the traditional competitive walls of the tech sector. SK Hynix, a memory giant, has partnered with TSMC, the world's leading logic foundry, to co-develop these new base dies on advanced logic nodes like N5 and N12. For the first time, a memory company is outsourcing the foundation of its product to an external rival. Meanwhile, Samsung is attempting to leverage its unique position as both a memory maker and a logic foundry to build a unified, in-house solution. The race is no longer just about who has the best design, but who can coordinate the most complex supply chain in human history. To understand why this transition is so difficult, we have to look at the brutal physics of stacking silicon. Imagine building a 15-story residential skyscraper directly on top of a raging industrial blast furnace. The residents upstairs represent the delicate memory cells, while the furnace below is the blazing hot logic processor running at 90 degrees Celsius. This is the exact physical reality of HBM4. Dynamic Random Access Memory, or DRAM, is highly sensitive to heat. It stores data as tiny electrical charges inside microscopic capacitors. As the silicon heats up, these charges leak out at an accelerated rate. Standard memory must refresh its data every 64 milliseconds to prevent data corruption. If the temperature of the memory stack rises past 85 degrees Celsius, the leak rate spikes, forcing the system to spend more time refreshing memory than actually processing data. By placing an advanced logic-based die at the bottom of the memory stack, we are placing a second heat source directly underneath these volatile memory layers. Because silicon is a poor conductor of heat and the layers are insulated by microscopic gaps, the heat becomes trapped. Without breakthroughs in materials science, like low-K dielectrics and novel thermal interface materials to draw the heat away, these next-generation accelerators will literally bake themselves from the inside out. For years, the standard way to connect stacked silicon was through tiny solder spheres called microbumps. You place thousands of these microscopic solder balls between the layers, heat them up until they melt, and let them cool to form an electrical connection. But as we scale to a 2048-bit interface, microbumps hit a physical wall. To fit twice as many connections in the same footprint, the spacing between these bumps must shrink to under 10 microns. At that scale, the physics of solder change. When you heat the solder, surface tension can cause the liquid metal to bridge across to neighboring connections, causing an instant, fatal short circuit. This is forcing the industry to abandon microbumps entirely and transition to copper-to-copper hybrid bonding. In this process, the solder is eliminated. Instead, the surfaces of the two silicon wafers are polished until they are atomically flat, with copper pads embedded flush within the surface. When these wafers are pressed together at room temperature, the ultra-flat silicon dioxide surfaces bond instantly. When the temperature is slightly raised, the copper pads expand and their atoms migrate across the boundary, fusing together into a single, continuous copper wire. This reduces the connection pitch to under 1 micron, allowing thousands of more connections without the risk of solder bridges. But it requires clean rooms so clean that a single speck of dust can ruin an entire production run. The transition to hybrid bonding and advanced logic-based dies has turned HBM4 into a logistical and security nightmare. Historically, a memory chip was built from start to finish inside a single manufacturing facility. But HBM4 requires a highly fractured split-fab manufacturing process. The memory layers are fabricated in South Korea. The advanced logic-based die is manufactured in Taiwan. These components must then be shipped across international waters to a packaging facility, where they are integrated onto a silicon interposer alongside the main processor. This hyperconnected supply chain introduces severe security and operational vulnerabilities. Modern smart manufacturing facilities rely on deeply integrated industrial networks. When factories across different countries must coordinate their automated transport systems and sharing of proprietary silicon designs, they expose their operational technology to potential cyber espionage and sabotage. A single digital disruption at any node in this multi-partner chain can instantly paralyze the production of the processors that power the global cloud infrastructure. As we look past the initial rollout of HBM4, even advanced logic nodes and standard hybrid bonding will eventually reach their physical limits. When the features on the base die shrink to the sub-5 nanometer level, conventional lithography cannot print the metallic channels precisely enough without creating electrical leakage. To overcome this, researchers are exploring experimental manufacturing techniques like atomic precision advanced manufacturing, or APM. This technique bypasses classical lithography by using scanning tunneling microscopes and chemical processes to place individual dopant atoms, like phosphorus, directly into the silicon crystal lattice. By manipulating matter at the single atom level, engineers can create atomically sharp metallic boundaries and ultra-conductive wires that do not suffer from the scattering effects that plague conventional copper interconnects. While still in the research phase, integrating these atomic-scale techniques into middle-of-line silicon fabrication is the next major frontier to keep the memory wall from closing in. For 70 years, the fundamental architecture of computers has remained unchanged. We built processors to think and memory to remember, keeping them physically separated. HBM4 changes this forever. By fusing advanced logic directly into the memory stack and bonding silicon at the atomic level, we are witnessing the end of the historical separation between memory and compute. The battle for leadership in artificial intelligence is no longer just about who can design the smartest algorithm or who can shrink a transistor down to the smallest fraction of a nanometer. The real victory will belong to those who can master the brutal, three-dimensional physics of packaging, managing the heat of stacked silicon, and forging connections at the atomic scale. The line between where the data is stored and where it is processed has officially dissolved.